Okay, we're just going to look at some basic examples in this video of finding some derivatives using the shortcut rules that we've just talked about. All right, so we will learn lots more shortcut rules, but so far this is what we have. And so we could certainly find these derivatives using that definition of the derivative with the limit as h approaches 0 and all that. But for basic functions like these, we don't want to have to go through that every time. So it's worth learning these shortcut rules. All right, so the big deal thing here is just sort of matching up what kind of function you have with the appropriate rule. So that's why I wanted to kind of do several different ones together here. All right, so we have 4 shortcut rules so far. The first one for a constant function. The next one is for a constant times x. We're differentiating with respect to x. This next one is for x to a power, so variable x in the base to a constant power. And then this last one, e to the x function, so basic exponential function with base e, variable in the exponent. All right, so I tried to put some things here that are kind of typically distracting for students that sometimes make them choose the wrong rule, so we can kind of talk about what to focus on. All right, so essentially you want to think about, do I have a constant function? Do I have a constant times x? Do I have a power function? Or do I have an exponential function? So paying attention to where your variable is. All right, so the first one is actually pretty easy, I think. It's a constant function. The output is 5 no matter what the input is. And so that is just this first shortcut rule. So I've got f of x equals 5 for my function. And so then my derivative for that one, f prime of x, or you could use df dx or any of the other derivative notations we talked about, is just going to be 0. Okay, one thing to be careful about, I've mentioned this in some other things as well, but remember this is a place where sometimes I see students starting to get sloppy, is that they will start with their function and then they won't write this part, they'll just write equals 0. And just think about that for a second. You then would be saying 5 is equal to 0, which of course is not true. So you don't want to write those kind of things. So this is the function, and this is its derivative, and they are not equal to each other in general most of the time. All right, so using good notation here, don't be sloppy in your notation because it can lead to sort of sloppy thinking, especially when you start doing more complicated problems. All right, so that one's pretty straightforward, constant function. And if you forget the rule, this one we talked about when we talked about why this rule is what it is. But for a constant function, you can kind of just think about the graph and think about slope. So f of x equals 5 is a flat line at 5, and just think about slope. The slope is 0. Right? So even if you forget the shortcut rule, you can remember that. All right, this next one sometimes is distracting to students because there's a square root there. And so sometimes they start thinking about things with square roots. Some of our later examples have things like square root of x in them and things like that. But the other thing I want you to pay attention to here is, where is the variable? And for this second function, notice there is no variable over here. That is just a constant function. So really, these first 2 examples are actually the same kind of problem. They're not the exact same problem, but they are the same kind of problem. They are both constant functions where the output is constant no matter what the input is. It's just a different constant for this one. So for this one, the output is square root of 2, and the slope is still 0. Okay, so for this one, I'm going to go ahead and write over here f prime of x equals 0. And again, you can use different notation for the derivative if you prefer. You want to be comfortable with all the kinds of different notation that we've talked about. All right, so sometimes students have done some problems like that, and then they look at this next one and they say, oh, 0 again. But the key thing I want you to zero in on every time you're looking at these problems is, where is the variable? Where is the variable? Okay, so where is the variable? All right, so in this case, I have a constant times x. This is a line, y equals mx plus b. The b is 0. This is a straight line. And again, on this one, you can think about slope. This is a straight line with slope 1/4. And remembering that that's what the derivative really is. So you can think about it in terms of slope. You can also think about it in terms of this shortcut rule. So the derivative with respect to x of constant times x, notice that's different than constant all by itself, constant times x is just that constant. So I'm going to here use the dy dx notation. I could use y prime, but just to use some slightly different notations there. Okay, so derivative of constant times x, just that constant, that's the slope. All right, these next three problems, I tried to kind of use some similar things in these next three problems just to compare and contrast a little bit and notice some places where students sort of make a mistake. And so I went through these and I circled where the variable is. You don't have to do that, but that's one of the things that you want to focus on when you're thinking about these problems is where is the variable. And notice on this last one, I didn't circle a variable anywhere. Right, so there is no variable here. Students sometimes get distracted by this because it looks like a power, maybe a power involving e, so they think it's like this problem here. But notice that there is no variable there. And so this last problem, in fact, is also just a constant function, right? So this is just a constant function. E to the fourth is, you can get a decimal approximation for that if you want. But, you know, 3-ish to the fourth power, something around 80-ish, right? So e to the fourth, that's just a constant, just like these other problems here. So this last one is kind of distracting, sometimes because it looks like a power, sometimes because of the e, but again, notice no variable. This is just a constant function. So this last one, I'm going to go ahead and do it. The derivative is 0, just like these first two, constant function. All right, these next two, I put them next to each other to contrast a little bit. So I have two rules here that involve things that look like powers, right? X to the n or e to the x. And the key thing to think about in those is that they have the variable in a different place, right? So it's just a matter of making sure that you're clear about which one it is you're working on and then using that appropriate rule. Okay, so this middle problem I have here, I guess, in my list of problems is y equals e to the x. Okay, so that's this one, e to the x, and that's the one function whose derivative is actually equal to itself, well, other than the 0 function, but the function that changes whose derivative is equal to itself. All right, so this is the one you could get away with writing equals e to the x for the derivative, but I'm going to label my work here and write that I'm thinking about the derivative over here, and that is equal to e to the x, right? So that there's not much to think about there. It's just identifying that that's the one you're working with. All right, this next one is x to the e, right? So x to a power. All right, so this is called power rule. We talked about why it's true. We looked at some other examples with things like x to the third and things like that when we first developed these rules. But here, for this derivative, I'm just going to recognize that that's what I have, x to a constant power, so variable in the base to a constant power. And I'm going to just apply this rule. And again, being careful to label my work correctly here. So dy dx equals, right, and then this is the kind of rule that a lot of students remember. If they don't remember anything else about calculus, they remember this rule. And so they'll say, oh, I bring down the exponent and subtract 1. That kind of describes what you're doing. But we're going to end up out front with e, that number, whatever that is, 2.7-ish, times x to the e minus 1. And you can't simplify this really anymore and leave it in exact form. If you wanted decimal approximations, you could get a decimal approximation for e and a decimal approximation for e minus 1 and put those in there. But in general, we want exact values. That's kind of the point. Maybe at the very end of a problem, you might round and estimate. All right, so these are some very basic ones. The next video has some slightly more complicated ones and then more complicated even after that. So keep watching a few videos and then try your homework after that.